Hi, welcome back to Cathedral High School in Academic Chemistry. My name is Mr. Kubuske. We're still in Unit 3. We're still talking about atoms. Today we're going to talk about something called atomic mass. In the last section we talked about the numbers that correspond to different elements, atomic number, mass number. We talked about how to calculate protons and neutrons from those numbers. We talked about what an isotope was when we changed the number of neutrons. We talked about what an ion was, whether positive or negative, when we changed the number of electrons. Okay, so when we did all that, there was a number on the periodic table I kept having you look up or refer to. If I look at this one right here for carbon, this 12.0107, that's known as the atomic mass. And I told you in the last section that, you just take that number and you round it to the nearest whole number, and then that's your mass number, okay? Which is true if it's the common isotope. But I didn't really tell you what the atomic mass was, what that red number actually represented with all those decimal points. So that's what we're going to do today. Okay, so let's talk about atomic mass. What is atomic mass? Well, atomic mass is the average mass of any element. And when we say any element, we mean all of the atoms of that element. Okay, we're taking the average mass of every single atom of oxygen, or every single atom of carbon, or every single atom of lithium. And we're going to take that average and put it together. Okay, now how would we do that? Well, what we need to know is the relative abundance of that type of isotope in nature, and I'll show you what I mean here in a second. Okay, and when we multiply those numbers together, the mass times the relative abundance, we add up the different numbers for each isotope, and that's how we come up with our atomic mass. And again, I'll show you in the examples here in a second. So it's a weighted average mass that reflects both the mass and the relative abundance of the isotopes, which means basically that this number should be closer to the common isotope rather than just an isotope. It's usually not a whole number, with the exception of carbon-12. Okay, carbon-12 is going to be exactly 12.0. We'll talk more about that later on. It's the number listed on the periodic table, and it's always calculated in something called AMUs, which stands for atomic mass units. Okay, so let's do an example quickly together. There's some people out in the hallway. We're switching classes right now, but besides the point. Anywho, so we've got two isotopes of lithium. We've got lithium-6, we've got lithium-7. Lithium-6 has an actual mass in AMUs of 6.015. Lithium-7 has a mass of 7.016. So if I just took the average of those two right now, it would end up somewhere in the middle, like 6.5. But remember, I have to take the relative abundance, okay, how much of it is actually found in nature, and I calculate that into the problem. So for lithium-6, of all the atoms of lithium on the planet, only 7.6% of them are lithium-6. The other 92.4% are lithium-7. So when I use that number, it should push my information either towards the 6 or towards the 7. Now, since I have more 7s, I would expect that my answer when I calculate my atomic mass will be closer to 7, because 92.4% of those are lithium-7. So that would mean that all that average is going to be pushed that direction. Okay. So here's how I do that. I take my number, my mass number for that one isotope, and I'm going to multiply that by its percentage. So 6.015 times, I can't just take 7.6. So what I do is I take that percentage and I make it back into a decimal by either dividing by 100 if you want to actually use a calculator, or you can just move the decimal point backwards 2 spaces. So it's 6.015 times 0.076. Because remember, if I move 2 decimal places, there's a 0 in front of that 7. So I take that number, and then I do the same thing for lithium-7. Its mass is 7.016. I don't change that, but I have to change the percentage, so it's 0.924%. Excuse me, just 0.924. I do the multiplication first, and I get 0.457 and 6.48. And now I add those two numbers together. I don't change them at all, I just add them. When I add those two numbers together, I get 6.94 AMUs, or atomic mass units. So that means the average of all of the atoms of lithium on the entire planet, the average weight is 6.94, which makes sense to me because that number should be closer to 7, since 7 is the common isotope. Okay, so lithium, again, if I looked at it on the periodic table, it's a 6.941, and I can look it up right here, and it says the same thing. So that's how that number is calculated. Let's do one more together. I'll do it up here on the board so you can see exactly where those numbers come from. Okay, let's do carbon. The most common isotopes of carbon are carbon-12 and carbon-13. There's some trace ones out there as well, but these are the two that are the most abundant. Okay, so again, what am I going to have to do first? I have to get a good marker, and then I have to take my numbers. So I'm going to multiply the mass of carbon. Carbon-12's mass, as you can see it on the screen, is exactly 12.00 AMUs. I'm going to multiply that by the percent in nature. Now the percent was 98.89%, but I moved that decimal point backwards 2 spots. So it's times 0.9889. Okay? Do the same thing for carbon 13. Carbon 13's mass, which is given to me, is 13.00. Okay? Well, I can throw the 3 on there, but it really shouldn't change it. Which is then times, not 1.11, but 0.0111. Okay? And again, that comes from moving the decimal point backwards 2 spots. And there's an empty place, so I fill that with a 0. Okay? So 0.0111. Now, I do the multiplication first. Okay, and I'll change colors so you can see it a little bit better. Okay, multiplication first. When I do that, I get 11. I'll write it down here so you can see it. 11.87 AMU for carbon 12. And then down here, I get 0.144 AMU. Now, when I add these two numbers together, the 11.87 plus the 0.144, okay, that should give me a total of 12.01 AMU, which is my atomic mass for all carbon. That's the number I'm going to use for all carbon. So let's check my work, see how I did. There you go, 12.01 AMU. That's how you calculate that number. Okay? Now, just a quick review. How do we calculate the atomic mass? It's the actual mass of an isotope times the percentage of it in nature. Okay, you repeat that for all, not necessarily the elements, but all the isotopes found in nature. So for here, it's carbon 12 and carbon 13. Okay, and then we add the totals together to find the atomic mass of all the elements, or all the atoms of carbon, or all the atoms of that particular element on the planet. Okay, that should be it. All right, that's it. Go try them on your own. Check your work online. Contact me if you have questions at gocathedral.com or mrkubuske.wordpress.com, and go Irish.